Back on track. I never paid attention. Rita takes notes.
I know. I did like
So
the first
good.
day, and I was like, I already know this.
Do you use the notes you take, Rita? Sometimes? No.
All right, everybody. I appreciate your patience. Since you're all highly observant students, I am not Lawford. I don't speak with a Texas accent. I'm not tall and lanky and sound like I just fell off a horse. All right. Having said that, you see I've already lost one student for the day. She's happy. If I'm not going to hear from Lawford, I don't want to hear it at all. No sense of humor, man. Before you guys kicked in this hall. All right, your tuition bills aren't that bad. Okay, my name is Rick Murray. Yeah, I got it. I'm a professor in earth sciences. I teach oceanography. Any people in my oceanography class before? No? All right, sorry. There you are. You too. All right. So Lawford is away, taken out of town for personal business. Emailed me up over the weekend, asked if I could pinch hit for him, and so here I am. Today we're going to be talking about shorelines and beaches and all this sort of stuff up in here. And we're also going to be talking a lot about hurricanes and tornadoes and things like that. A lot of mayhem today. Today, I went through the lecture over the weekend. It's sort of like mayhem, flooding, roofs blowing off of houses and stuff like that, and so on.
Yes, it is actually.
Okay, so we need to learn about waves. And I will say, it is a little hard coming in just sort of parachuting into a lecture like this. I don't know what you've had before, so I'm going to ask you guys, have they seen this before?
No.
Okay. All right. Waves and wave base. Very important concept in geology, environmental science, oceanography, and what have you. But your waves have a motion direction, as you can see here with these arrows. And as you recall from any time you've been at a beach and a wave goes by and you're floating, you move up and you move down, but you also move in a general circular motion as the wave comes and moves you towards the shore, and you go up and then you move away from shore. And your body, if we consider your body as a particle, and don't take that personally, but if we consider your body as a particle, you're going to be describing a circular motion. And as you go further down in the water, away from the energy of the wave, that circular motion particle gets smaller and smaller, eventually to a point. Eventually to a point where. Eventually to a point where you reach what is called wave base, and that's the point below which there's no more motion. There's no motion at all. All right. Now that's a wave that's out in the sea, where it's not impacting and landing on the shore yet. As you know from being at beaches, waves do hit beaches, and they are fun, but they also can cause destruction. But here's what comes up with a wave. Out here we have the same diagram that I just had on the previous slide, and this wave is going to come in and land on the beach. And you'll see at some point the shoreline creeps up, the water depth shallows creeps up to where the wave base intersects the shore, right here. And at that point, those very small circles of motion are going to be dragged onto the sediment. And there's friction there. Water is a fluid, but it is a physical entity, so it has a frictional coupling with the surface of the seafloor right here. And that's going to slow it down. Friction slows things down. You fall off your skateboard or your bicycle and you hit the asphalt, you know friction slows you down. That's friction, otherwise you just skid forever, right? So friction slows down, and this is shown pictorially here by these circles lagging behind the top circle. The top circles are not affected by friction. The wave keeps moving this way. The energy gets more and more compressed as the sea floor rises up, and eventually the top of the wave falls over. The top of the wave falls over. It gets too far ahead of itself, The bottom is dragged by friction. The top of the wave gets too far ahead of itself, and it essentially falls over. So this picture here is very important because it describes several things, not the least of which, or perhaps the most important of which, is the fact that there's friction between the bottom of the wave and the seafloor here. Now, this is why a big wave, if you're on shore at a beach during a storm and you look hundreds of yards out at sea, a big wave is crashing. And this sounds very stupid to say, but it's true. Small waves only crash really close to shore. Big waves crash further away from shore. The reason for that is a big wave has a deeper wave base, so this whole process starts further offshore, and then the result is the big waves crash further offshore. A tiny little wave like this, teensy little wave coming in, it's only going to hit wave base very close to shore, and then it'll just go poof and fall over. But it's the exact same process in a puddle on Commonwealth Avenue, or on a regular beach, or on a regular beach during a big storm. It's the same fundamental process of circular motion getting compressed and friction slowing it down, and then the wave crashes up on the shore. This water moves up the beach because we're translating energy into the water motion itself. The energy of that wave propagating up onto the shore, it crashes, and that energy turns into the movement of mass. Conservation of mass, conservation of energy, as we say, not just a good idea, it's the law. So this energy, as this is moving forward and the wave crashes, turns into the motion of the water up and down the beach. All right, any questions about that? So friction is key. So this leads to some interesting situations, which we'll discuss here. It's very rare that actually the wind direction that's driving waves is exactly parallel to the shore. All right? I mean, think about that. The shoreline moves around, it's got structure, it's got little embayments, it's got promontories. Beaches, some beaches are true north-south, some are just a little bit off to north-south, some are east-west. Right? And it's not like every beach happens to miraculously be parallel or rather orthogonal to the wind direction. Yet, as you know, waves tend to crash onto the beach directly parallel to that beach. Yet it's the wind driving those waves. So why is it? What process is going on to cause those waves to always crash parallel to a beach? And that's called wave refraction, which leads to something called longshore drift. Consider these waves here in these diagrams, and they look like they're coming in a little obliquely, okay, which they are. All right? But this wave right here, let's take a look at this one right here. This side of the wave here on the right is going to hit the beach first. That's going to cause it to slow down over here, because remember, underneath the water, right along this part here, that wave is feeling bottom, wave base is intersecting bottom, friction is causing it to slow down. So this part of the wave here is slowing down. This part of the wave on the left side of the diagram is not yet slowing down. It's in deeper water. It is not yet feeling bottom. Wave base has not yet intersected the bottom. So this is slowing down. This is still going faster. And so the whole wave is going to basically do this. My right hand is going to slow down. My left hand is going faster. It's going to curve like that. This whole thing is going to sweep up in this direction. Because the right-hand side slows down while the left-hand side still moves fast. That causes this wave to become parallel to the shore. Because the part that hits first has more friction at first, slows down. The left-hand side is going faster, and it's going to curve in. The whole thing is going to go like this. All right? And then become more parallel to the shoreline. That's why basically, whenever you're on shore, by and large, the waves are coming directly at you. Next time you're at a beach, if you can, look out to sea 4 or 5 miles, or 2 or 3 miles, or as far as you can. And you'll often see waves going by you from right to left. And it's like, well, what the heck are those waves doing? They're going that way out there, and they're coming right here. Well, they're a little oblique, and as they hit shore, they curve, and they come down, and end up going parallel to the beach. All right? Now, the other thing going on is they're not exactly parallel. I mean, the world is never exactly like Euclid. All right? It's not perfectly parallel. So what's going on here, you can see as this wave comes in, sand grains are going to move up this way due to the effect of the wave. But then when the wave goes by, the water rushes back out, the sand grain is going to roll downhill. Gravity never takes a holiday, so the sand grain is going to roll downhill. And so slowly you're going to see that sand grain rolls up from the wave, rolls downhill due to gravity, rolls up this way from the wave, downhill due to gravity, and so on. And that's called longshore drift, sort of along shore. Along the shore, the beach sand grains move, in this case, from right to left. All right? So that's a function of the wave energy. Here we have an air photo. That's the wing of an airplane or a helicopter. It's like actually an airplane. Okay? And there's a difference between waves and swells. And what you can see here is you can see both. See these large structures here. I'm going in this direction. Those are large swells which are caused by distant storms. Distant storms may be 500 miles away, 1,000 miles away, cause large waves. Large waves travel across the ocean in response to that big effort. You can see at a little angle across here, the smaller waves, and they're not headed in the same direction. Those are caused by local wind. So you can have large swells and then smaller waves superimposed on top of those swells. And they often cause interference patterns between them. And sometimes they can end up going in the same direction, so you'll have a small wave on top of a big wave, which will lead to an even bigger wave, and so on. Big waves, for reasons, if you took my oceanography class, you'd know, big waves travel faster than small waves. So that's why big waves are from distant storms. And you often hear that in the weather report. If there's a hurricane off Bermuda, they tell us to be very careful when we're swimming around here. You think, well, what does a hurricane off Bermuda have to do with us? Well, it's a big storm, causes big waves. Big waves travel fast and further. And so you end up with swells coming from a large distance, and waves, wind waves, being local from a close distance. Here's a nice air photo showing the wave refraction that I was talking about. And you can see the waves out here are almost like this. And you can see them as they wrap around and become more and more parallel as this side up here is slow and this side here is fast. So the wave is slowly doing this. It's torquing around as a pivot point up here and becoming more and more parallel to the coastline here. Okay. It gets more complicated when you have not just a nice smooth beach, but if you have a promontory sticking out like this, a point or an island, and you can see how these waves are coming in through here. And you see on the side here, it's being slowed down by this island and the beach underneath the island here. okay, the seafloor underneath here, and it's being slowed down here as well. So in the middle, the waves are moving faster, and on the edges, it's slowing down, and on the edges, it's slowing down here. These points of land, and there's a photograph I'll show you later in this class, these points of land actually end up being constructed and caused by waves, by wave refraction. Because imagine a wave coming in here, say it's perfectly parallel, and it's having a path like my red pointer. So the wave is coming this way, the wave front is like this. This part right here is going to hit first. This part's going to hit next. This is faster. That wave is going to curve around and become parallel to this shore. So the wave is going to come in and curve around and start eroding here. On the other side, you've got the same thing going on. The wave's coming in. It's going to slow down here. It's going to remain fast here. It's going to curve around and start focusing here and here. So a point that's sticking out into the ocean is going to be further constructed and further emphasized by those waves, because the wave is going to slow down at the tip, and you're going to focus the erosion on the edges of that and cause that point to become even more prominent than just the parallel beach itself. Okay. Which direction is the longshore drift here? Point. Everybody point. We're not doing clickers today. I guess Lawford does clickers. We're not doing clickers, but you still have hands. So move your hands. This way or this way? All right, it's going this way. All right. How many said that way? Okay, you're wrong. But that's good for being open about it. All right, the reason why it's going this way is because imagine yourself being a sand grain. All right, you're just hanging out doing your sand grain thing, whatever sand grain does, sitting right there. This wave is going to move you up in this direction, exactly perpendicular to the wave. But then that beach slope is going downhill. Gravity is going to cause it to move down this way again. So your sand grain, shown here in red, very large, very bright red sand grain. Pretend it's a ruby, I guess. It's going to move up and then down. Up, down, up, down. Up in response to the waves, back down due to gravity. And the overall net transport is going to be in this direction, like that. Okay? All right. So, a bunch of slides. Sand in motion. This is a cliff sort of along the beach. What is the origin of the sand? Very clearly, this incised river channel. You can see this river is eroding from the croplands here, and the sand is getting delivered down to the beaches here. And you can see these little plumes of sand. The current is moving in this direction. There must be other examples of rivers like this all up here, and so on and so forth. And you can see the longshore current drift going down in that direction. Okay. Here are two slides. In case you don't know, that's sand on a beach. Those are people. This is in La Jolla, California. Sometimes if you have high storm activity, all the sand goes away. This is the same place. High storms, or if you dam the local river and thus block this sediment from being delivered to the beach environment, if you for some reason interrupt the erosion, interrupt the delivery of sand to the beach, you end up what starts off to be a nice beach and has no more sand associated with it. This is exactly the same place. I had looked at this morning, I was looking at this back to back. See that right there? Whoop, that's it right there. And then that block, that's that block. So this is exactly, blah, blah, blah. Sorry, I can't really translate. There's that. Okay? Same place. If you remove the source of the sand, that's what's going to happen. Okay, let's talk about groins. No, not that. Groins are what are called these man-made devices, structures, often called jetties, that stick out and are designed to stop the longshore transport of sand. Well-intentioned engineers that see that the fact that, hey, all the sand is going away, so let's put these sort of barriers in to trap the sand and prevent it from just getting longshore drifted out of our system here. You can clearly see what direction is the longshore drift here. Up or down? Who thinks it's going this way, which we'll call up? And who thinks it's going down? Everybody raise your hand if you think up. Up. Raise your hand if you think down. Okay. It's going up. Why is it going up? Why is it going up? Someone yell out. Someone who said up, because you're right.
Because the sand is being pushed against the jetty. Pushed up.
There we go. Thank you. Perfect. I was confused as to where that was coming from. Thank you. I was like, wow. Good answer. Perfect. Okay? So the sand is rolling down in this direction, and it gets stopped here. All right? Now, you notice there's not much sand here because it's rolling in this direction, and it's not being replenished. It's not being rejuvenated because this groin is keeping it stopped. All this sand here is piling up right there. Okay? Another good example. Here you can see it. Longshore drift coming this way. Boom, piling up. This point here is further out to sea than this point there. All right? And here's a figure, I guess, from your textbook. Shows exactly the same thing. Here's your longshore drift. Here's your wave refraction as well. You can see the sand piling up, and then you've got a starved beach here. All right? Often on these beaches, commonly in California, Florida, other places that there's nice beaches to lie around in, this is where everybody goes who knows what's going on. All the tourists are down here because they don't know the local setting, and these beaches are nowhere near as well developed as these here. Okay? There can be significant dollars spent on this. There are significant misunderstandings of how things work. Here's the Santa Barbara Marina. So obviously they wanted to put a marina here. They put some levees and all this sort of thing to protect the vessels. But they end up trapping the sand on the outside, and so you end up needing to continually dredge the marina because the longshore drift just keeps bringing in the sand to fill in the harbor. Okay, this is probably one of the most important parts of the lecture because this might save your life. And when I talk about this in oceanography, I say, look, I know you all want to be oceanographers and you got up in the morning all excited about this class, just hoping for this class. But truly, what I'm going to say in the next 5 minutes or so might end up saving your life because if you don't end up being environmental scientists or oceanographers, you're probably going to be at a beach someday and you might get caught or your kids might get caught in a rip current. So pay attention because this might save your lily white behind on if you're ever out on a beach someday and get stuck in a rip current. All right, so here's a rip current. Who knows what a rip current is? What's a rip current? Way in the back row. Yeah. All right, ocean goes around and circle by the shore instead of, say, just coming out in the middle. Sort of, not bad. I appreciate you raising your hand and letting me yell at you. You're back. All right, so see this white stuff here, and you see this current coming out here. A rip current is what happens when you're bringing in a lot of water with waves. That water and that energy has to go somewhere. And it's a mass balance. Water comes in, water has to go out. Not all the water that comes in a wave just sloshes back out with that same wave. You have to have a mechanism to move a lot of that water that the waves are continually bringing in to get that water back offshore again. And a fluid, there's a result from fluid mechanics that leads to what are called rip currents, which are narrow focused currents moving water offshore. And they can be relatively regularly spaced, as you see here with this white. And I'll show you a bunch of really good examples. Old Wofford's got some good examples here. Here's another. This is where the circular motion from the woman in the back row was speaking of. You'll see here, this rip current comes out and kind of curves around. All right? Here are people hanging out on the beach. You see, here's longshore transport. So you've got a big beach here, people hanging out, swimming, and there's a rip current right here. And something to be careful of, which we'll show you. Famous Zuma Beach near LA. Rip current, you see moving it out. Here's some people, also known as particles, being moved out in the rip current. And look at this. You can see there's a rip current here, rip current, rip current, rip current. Important thing for you to remember, rip currents are not abnormal. It's not something that rarely happens. They're everywhere. They're part of the normal functioning behavior of a beach. Sure, at times they might be more present than at other times, particularly if you've got a lot of big waves. A lot of big waves are bringing in a lot of water. You're bringing in a lot of water. You have to move a lot of water offshore. So here's what you do to survive a rip current. Okay? Here we have a beach. Here you have the picture of a rip current coming out, water moving out. It's very, very common. I was stuck in a rip current about 5 years ago. I certainly know what a rip current is, but you know, my urge to survive kicked in, and I started doing exactly the wrong thing. Okay? I didn't panic, but I was like, I don't want to be going this way, I want to go that way. And I started swimming in. Okay? And you will not make it if you keep swimming in, because these rip currents are going out far faster than you will be able to swim. Okay? So what you should do is you should do two things. One, start swimming parallel to the beach. Don't try to swim fast. Just swim steady parallel to the beach. All right? Seriously. You might go as far as a mile offshore. Those photographs that I showed you from the lecture here, those are itty-bitty little ones. Okay? That sometimes happen. Some larger ones, you'll go out like a mile offshore. But if you're a good swimmer, you don't panic, you don't freak out, and you don't waste all your energy trying to swim against this thing, you'll be all right. Just swim parallel to shore. It doesn't matter. Don't sit out there and go, what the heck did that Murray guy say about longshore drift and the current going this way? Doesn't matter which direction you swim. Just swim parallel to shore, and you'll eventually get out of it, and then just gently swim in with the waves on the other part of that circle that that woman was talking about, because you do see there's kind of a large-scale pattern there. All right? Might save your life. Remember that. And these things can really pick up all of a sudden. They're ephemeral. They won't be long-lived. You'll be swimming, and all of a sudden you'll find yourself getting pulled out to sea a lot faster than you thought. Don't worry, if you're on the East Coast, it's not going to bring you to Portugal. Just swim sideways, and you'll be all right. All right, changing subject matter here. Moving on to some uplifted shorelines. As you know, the Earth is very tectonically active. There's all sorts of other effects going on, like when glaciers happen and then glaciers melt, they release weight, and shoreline will start to rise. Tectonics happen, compression of plates will cause land to rise, and so on. Now, these uplifted shorelines provide beach material because you're eroding rocks and so on, but they also provide cliffs and all sorts of interesting shoreline features. Okay? Particularly in California, which is, as you know, with the San Andreas Fault, and the boundary between the North American plate and the Pacific plate is very geologically active, and you get these grandiose, stunning beach vistas that are a product of erosion as well as tectonism. Okay? You get features such as this. Here you have a bench. It's called a wave cut bench because the waves are actively crashing here. This is at lower tide. During high tide, waves are crashing and focusing all their erosional energy here and not so much up here at the top of the diagram. You can get sea arches. These form by that focused erosion that I spoke of, how the wave refraction is curling around and focusing the energy, like you can see here. All right, so the wave refraction, like we saw earlier, focuses that energy on the sides of the point, ends up causing all sorts of interesting features such as a sea arch and a stack. This is from the chalk cliffs of France. This is essentially the white cliffs of Dover, but on the other side of the English Channel, all right, over in France, where all those crazy French people are. Similar features, okay? And